This is a quick refresher video on how to identify the rank of a matrix using row elimination methods. So remember, rank means quite a few things. One of the things that it means is that it's the number of non-zero rows after you perform row elimination steps in order to get into row echelon form. And so row echelon form is the form where all of the zero rows are at the bottom, and that every leading entry in a non-zero row lies in a column to the right of a leading entry in any row above it. And so that just means that it has this somewhat diagonal structure. So it doesn't necessarily mean that everything has to be on the diagonal. For example, it could be 1, and then 2, 3, 4, 5, and then you could have 0, 0, 1, 2, 3, and then 1, 2. And so that means that, again, there's more than 1 0 here that we've added. So it's not exactly on the diagonal, but that they are in this kind of diagonal structure so that everything is at least to the right of that. And so in order to get into that form, you use row operations. So you can make 3 different operations. You can swap 2 rows. You can multiply a row by a constant, a non-zero constant, and then you can multiply one multiple of a row to another. And so this is a very systematic way of identifying the rank of a matrix. It's simply just the number of non-zero rows that are left after you go through this process of row echelon form. Another way of understanding rank is that it is the number of linearly independent rows, or it's the number of linearly independent columns. And so I'll try to give you a little bit of a sense of that. And it's actually row operations are really exposing the dependency of certain rows and or columns. So this is a 4x5 matrix. Many of the matrices we'll be looking at will be square, but just for generality, I'm going to show you this 4x5. So there are a couple things that we can observe. And so we can observe that the highest rank that this matrix is going to be able to achieve is 4, and that's because it only has 4 rows. Even though it has 5 columns, we know that some of the columns need to be dependent on each other because we only have 4 rows. And so it's the number of linearly independent rows or the number of linearly independent columns. And since rows is smaller here, that's what constrains the rank. So we can automatically see that there are 2 columns that are identical. And that's a very easy case of identifying dependency. So those 2 rows are not independent of each other. And we can also see that the second row and the last row are just a multiple of each other. So there's just a -1 that multiplies 1 to get the other. So that's another example of a simple dependency. And so you can start to see this, but it turns out that there's actually more dependency. So this identifying these 2 dependent rows, or rows that are related to each other, this automatically tells us that the rank is going to be less than 4, and in fact it's going to be less than or equal to 3. So what turns out is that there's another dependency in the rows that it's harder to see because it's a multiple of multiple rows combined. So to do row operation, we decide to eliminate certain entries. So essentially we want to get that kind of diagonal structure. And so if I leave this row here, then I'm going to use that row in order to get rid of the entries in the third row. So I want to get rid of that 3 because that doesn't obey this definition of row echelon form. So I'm going to take 3 times the first row and subtract it from the second row. And the important thing is to do this across the entire row. So 3 minus 3 times 1 is 0. And so that's the whole point of doing this. So I get 0 in this entry. Then I take -2, and I subtract away 3 times -1, and that gives me a +1. Then I take 3, and I subtract away 3 times 1, and that gives me 0. I take 1 and I subtract away 3 times 0, and that still gives me 1. And I take 7 and I take away 3 times 3, and that leaves me with minus 2. And so at this point, now we have this new matrix, which, although it has different entries, it has the same rank. And so that's the important thing about the row operations, is that it doesn't change the rank of the matrix. And so immediately, now we can see that this row and this row are identical, and this is a -1 multiple of those rows. So here's where we can easily see the dependency again, now that we've subtracted away this operation. And so now this reveals the dependencies even more. And so what this is really showing is that row 3 was actually equal to 3 times row 1, and then plus 1 times row 2. And so that indicates that there's a dependency, because we can write one of the rows in terms of the others. And so if we continue our row reduction, or to put this in row echelon form, then I'm going to multiply the second row by a -1 and add it to the third row, and that's going to essentially eliminate that entire row. And then I'm going to add row 2 to row 4, and that's again going to eliminate that row. And so after these two next row operations, I have 2 0 rows now in my matrix. Again, the matrix is different, but it has the same rank as the original matrix. And so now this is in row echelon form, because essentially this leading term is to the right of any leading terms above it, and all the 0 rows are at the bottom. And so the number of non-zero rows is 2, and so that is the rank of this matrix. So like I said, we observed one easy to find rank deficiency, so we knew that it was going to be less than or equal to 3, and now we can say for sure that the rank of this matrix is equal to 2.